Dear friends, today we will discuss the principles of exploration that includes geological, geochemical and geophysical methods. Mineral exploration aims to discover deposits of minerals and rocks that can be used to meet the resource needs of the society. It encompasses the search for industrial raw materials, for example, clay, limestone, sulfur, salts and fertilizer minerals and rocks. Ores from which metals are extracted, for example, iron, copper and zinc ores, and gemstones that includes diamonds, sapphires and opals, and includes the search for solid fuels like coal, oil or oil shale and uranium, but not liquid or gaseous fuels like petroleum and natural gas. Mineral exploration can be as basic as prospecting using elementary techniques such as spanning for gold, or it can be very sophisticated also, involving the use of complex technology for data gathering and interpretation. This material considers our need for mineral resources, why different groups explore for minerals and the strategies they adopt and the tools they employ. What success and failure mean in the industry, the role of governments and the future of exploration. Human beings have always been dependent on natural materials to satisfy the needs of everyday life. All these materials must come from earth, either grown as plants or animals or extracted as rocks, minerals or fossil fuels. Some of the rocks and minerals that are important in everyday life are readily available, but many are not, as we must search for them. That search is what exploration is all about. The importance of rocks and minerals to humankind is conveyed by terms such as Stone Age, Bronze Age, Iron Age. The emphasis on stages in the evolution of technology and civilization is related to our mastery of different rocks and our understanding of the metals that can be extracted from them. In modern civilization, however, there is amazing diversity in the rocks and minerals we use and in the variety of ways in which we use them. Some mineral resources are used directly with little processing apart from shaping, polishing, crushing or sizing. For example, rocks used for building aggregate, used for road making, talc used in talcum powder or gemstones used in jewelry. Many mineral resources are consumed in industrial processes that transform them into new products. For example, clay is used to make bricks or ceramics, silica sand used for glass making, limestones used to make lime or cement, or phosphate rock used for superphosphate fertilizer. The large group of rocks we call ores, for example, iron, copper and gold ores, are important because of the metals they contain. Other rocks and minerals are used in industrial processes because they aid the process of other materials, not because anything will be extracted from them. For example, many rocks and minerals are used as flux in smelting. Who explores for minerals and why? The motivation for mineral exploration is the same as for many other human activities. Either we need the materials we seek, or by satisfying other people's needs we can earn money. Though exploration is necessary to maintain the supply of essential raw materials, individuals or corporations undertake exploration for a variety of reasons, but underlying them all is the belief that there will be a good commercial return from what is discovered. The commercial return may come from seeing or selling the deposits that are discovered from setting up a company based on the discovery and trading the company's shares, from starting a mine and selling the products, or from using the products as feed in some downstream business based on the commodity and profiting from sales of those new products. Companies of different sizes have different objectives and reasons for exploring and target different commodities and styles of mineralization. Coming to the exploration tools, the wide variety of exploration techniques available for exploration can be broadly grouped into three types. That includes geological, geochemical, and geophysical. The selection of the technique or combination of techniques used varies with a target sought, the area to be explored, the geological conditions, and the stage of exploration, the weathering regime, and the factors such as location, topography, vegetation cover, climate, and social and cultural issues. Some techniques can be applied over large regions, whereas others can be applied only over smaller areas. Some require a detailed ground access, whereas others can be flown by aircraft and require minimal ground access. The following discussion focuses mostly on exploration for metallic ore deposits. Because of them, the discovery of economic tonnage and grade is typically the crucial step. For many bulk commodities, especially most industrial minerals or materials, discovery is important, but the ultimate value of the find relates less to grade and more to marketability, which involves many different characteristics such as physical properties, amenability for the ultimate application, and presence or absence of deleterious impurities. Thus, the relative importance of the early search and discovery stages and the latter testing and evaluation stages changes with the commodity sought. If the geological situation in which the mineralization is likely to occur can be recognized by observation, then geological mapping of the rock types, stratigraphy, or structure can be used. Work on very prospective areas may involve more detailed studies, including petrography, fluid inclusion studies, or alteration mineralogy. Geological techniques are applicable only where geological observations can be made, that is, where there is sufficient outcrop or where appropriate samples can be collected, or where geological inferences can be made indirectly from aerial, geophysical, or spectral surveys, aerial photographs, satellite image, etc. Coming to the geological mapping includes systematic mapping of surface rocks or rock types, structures, hydrothermal alteration, etc. It covers all regional scales available globally, whereas the obtained coverage is very limited. The applicability requires reasonable distribution of exposures of bedrock, though other tools can be used to fill in missing information. It is an important tool in exploration for all deposit types, providing the basis for interpretation of all other data sets. Next is aerial photograph interpretation. A stereoscopic view of Earth's surface is provided by overlapping photographs. Lineaments, color, structure, weathering pattern, and vegetation can be used to generate a geological interpretation. Global coverage is available in this with valuable resolution and quality. It is applicable if the surface is visible, that is no cloud cover. It is best in areas lacking thick vegetation cover, an important add to geological mapping, and can be used to locate ore bodies that are exposed at the surface and show distinctive features. Next is satellite image interpretation. Satellite based scanners generate detailed images of Earth's surface. It is global and available everywhere, but application varies with density of buildings and agriculture, vegetation, rainfall, weathering, etc., and most useful in arid, well exposed regions An important aid to geological mapping can seldom be used to locate ore bodies directly, but in favorable conditions in remote areas can highlight alteration zones also. Next is spectral data interpretation. A wide variety of spectral information is now available from satellites, aircraft, and ground surveys. The coverage is global for satellite systems, large areas from aircraft, and small areas with ground instruments. Applicability varies with density of buildings and agriculture, vegetation, rainfall, weathering, etc. Most useful in arid, well exposed regions, and it is also useful aid to geological mapping in favorable conditions and can locate hydrothermal alteration related to mineralization or rarely large mineralized areas. Geochemical techniques involve the chemical analysis of geological materials such as stream sediment, soil, rock, and in some cases water, vegetation, or air. Analytical results, that is anomalies, may suggest prospective areas. Geochemical techniques are applicable only where the rock that hosts the ore or material derived directly from it is accessible. Sampling of overlying transported material, for example glacial debris, is not effective unless the source of the transported material is known, or unless chemical elements related to mineralization has migrated up through the transported cover. In areas of shallow cover, drilling may be used to collect samples from beneath the cover. Proper orientation surveys are essential for effective geochemical surveys. These involve testing of the responses of known mineralization in a similar nearby area to verify the effectiveness of the method under the prevailing conditions before using it routinely to look for unknown mineralization. Soil geochemistry. Systematic sampling of soil, usually of a selected size, fraction, etc. It covers two large and small areas depending on sampling density, and this is applicable in areas with residual soil, a very commonly used method in most metallic deposit styles. Next is rock chip geochemistry. In this kind of geochemistry, the systematic sampling of exposed bedrock as composites of small chips covering small areas only and requires extensive exposure of bedrock used in most metallic deposit styles. Next is the bedrock geochemistry. Bedrock geochemistry requires systematic sampling of upper parts of the bedrock, usually by drilling through shallow cover. It covers large to small areas depending on the sample density and depth of the cover. Applicable in areas of strong near surface leaching or covered by transported overburden used in most deposit styles. Stream sediment geochemistry. This is a very interesting kind of the stream sediment geochemistry and requires a systematic sampling of stream sediments, usually of a selected size fraction. It covers large areas and it has an application to small areas also, and may be limited by the stream pattern density, widely applicable in regional exploration, and requires bedrock outcrop or show subcrop used in most metallic deposit styles. Next is water geochemistry. Water geochemistry involves sampling of water in streams or wells or boreholes and may be applied over larger areas. Sample density is typically low. The applicability depends on the access to water samples in streams or bores. It has limited application for base metals and uranium deposits. Next is soil gas geochemistry. Soil gas geochemistry requires systematic sampling and analysis of gases trapped in soil. It covers mostly small areas. Sampling density is very high. It is suitable for areas with deep soil and transported cover, and it locates structures and may help to find some sulfide rich deposit styles. Next is the plant geochemistry. Plant geochemistry involves sampling of one plant species or part of one plant species followed by chemical analysis, that is mostly after ashing. It can be used mostly over restricted areas and best in areas with high plant density but low plant diversity, usually temperate to cold areas and for most base metal deposit styles. Geophysical techniques rely on variations in the physical properties of the mineralized rocks or the rocks that surround them to indicate the location of mineralization directly or indirectly. The physical response may be a direct property of the rock, for example, its density, natural radioactivity, magnetic properties, or resistivity, or an induced response produced by exposing the rock to a physical stimulus such as an electrical or magnetic field. Geophysical techniques may indicate mineralization directly or may allow the search areas to be reduced to a favorable host rock or a favorable structural environment. With the increasing availability of large-scale surveys, often involving more than one technique, the data from geophysical surveys can be interpreted to produce geological maps and to identify favorable settings for mineralization, exactly as they would be from conventional geological maps. A major advantage of geophysical techniques is that they can detect responses from mineralization but reach several hundred meters below the ground surface at depths too great to be reflected in the surface geology or detected by geochemical surveys. Next is the recognizing targets. Sometimes the ore bodies are exposed at and their surface expression can be recognized by explorers. But as exploration continues, new surface targets become fewer and fewer, and increasingly there is a need to look for more subtle targets. That typically involves the use of multiple exploration tools. The data from all the techniques to be used are compiled onto the maps, and the strength and location of anomalies in each techniques are compared. Areas that stands out with coincident anomalies from more than one techniques are usually priority targets for drill testing. One additional geological tool universally used by modern explorationists is the ore deposit model. There are models available for a wide range of ore deposit types, and new ones are regularly developed. These models summarize all the important geological characteristics, including a spatial relationship of a particular deposit type. Models include large-scale aspects such as the tectonic and structural settings. Next is the magnetic tools. The magnetic tools measure spatial variations in the intensity of Earth's natural magnetic field. It covers very large areas covered by aerial surveys, smaller areas by ground surveys, widely used as an aid to the geological mapping, also a direct detection method for some deposits, and it is applicable wherever rock magnetic properties vary. All deposits with a well-defined geological setting in magnetically variable rocks, direct detection of the deposits pointing or containing magnetic minerals, for example, iron ore, chromite, diamonds, and some volcanic massive sulfide deposits and some porphyry copper deposits also. Next is the radiometrics. Radiometrics measures spatial variations in the intensity of natural radiation from potassium, thorium, and uranium. It covers very large areas by aerial surveys, smaller areas by ground surveys. It is widely used as an aid to geological mapping, also aids directly detection of some deposits. It is applicable wherever there are variations in abundance of natural radioactive elements. All deposits with a well-defined geological setting, direct detection of deposits containing uranium or thorium minerals, or deposits with strong potassium enrichment in alteration zones, for example, some volcanic massive sulfide deposits and some porphyry copper deposits, and some epithermal gold deposits also. Next is the gravity. Gravity measures spatial variations in the intensity of Earth's natural gravitational attraction. It covers very large areas by aerial gravity gradiometer surveys, smaller areas by ground surveys, huge areas covered by very low density ground surveys, limited coverage with high resolution aerial surveys also. Detailed ground survey only in areas of low topographic relief. It is applicable wherever rock density vary. It is direct detection of deposits with strong density contrast to surrounding rocks, for example, iron ore, volcanic massive sulfide deposits and kimberlites. Next is electromagnetics. Electromagnetics measure the induced response in the earth from an applied electromagnetic field. Very large areas covered by aerial electromagnetic surveys, smaller areas by ground surveys. It can be used as an aid to geological mapping and also aids in direct detection of some deposits. Applicable wherever there are variations in natural rock conductivities, direct detection of deposits with high concentrations of conductive minerals, for example, volcanic massive sulfide deposits or VMS deposits, manganese deposits, etc., or where there are associated anomalous conductivity zones, for example, some porphyry copper deposits and kimberlites. Next is induced polarization. It measures the induced electrical polarization response in minerals from an applied electrical field. Ground technique mostly applied over smaller areas, but large surveys are also possible. It detects the presence of polarizable minerals, mainly pyrite, pyrrhotite, galena, chalcopyrite, etc. Direct detection of deposits with high concentrations of polarizable minerals, for example, volcanic massive sulfide deposits, porphyry copper deposits, etc. Next is resistivity. It measures spatial variations in the resistivity of the rock mass being surveyed. It is mostly applied over smaller areas. It detects variation in the resistivity and used in sulfide rich mineralization which has low resistivity compared to the surrounding rock, and can be applied to direct detection of sulfide rich masses, for example, massive sulfide deposits. Next is seismic. Seismic records underground surface reflections produced by explosions or mechanical thumpers at the surface. It is applied over huge areas for petroleum exploration, seldom used in mineral exploration, and indicates surfaces in the bedrock, for example, faults, beds, igneous layers, etc. It is used in mineral exploration, mainly used for layered complexes, for example, bushveld, and for engineering purposes also. Coming to the future of exploration. Mineral exploration is an essential part of the process of supplying the resource needs of the society. While that demand continues, so will mining and the exploration, and that is needed to sustain it. But exploration faces many challenges and is currently undergoing major changes. With the rise in the environmental awareness in the second half of the 20th century, mining was widely criticized for its environmental impact. Much of that criticism was justified, and there have been major changes such that the modern mining industry can now operate with minimal environmental impact in the area surrounding mines. However, it is inescapable that any process that takes material from one place to another must have an environmental impact. Mineral exploration has also come under attack by environmentalists, but most parts of the exploration process have very little to no environmental impact. Most opposition to exploration is either transformed or misinformed about what is actually done, or more commonly is based on the fear of what might happen in the unlikely event that a discovery is made leading to the mining. In fact, most exploration efforts leave no long-term trace and make no discoveries, even when targets are identified. On further testing, less than 1% proved to be of economic interest. The mining industry as a whole, including exploration, has been criticized for not returning a satisfactory profit on money invested, but such analyses can only be sensibly done on a case-by-case basis. Over the past decades, major changes have occurred in financial markets and in how business operate, with emphasis on short-term financial performance. Because exploration cannot guarantee very quick returns, it lost favor with the investors, with the result that in the late 1990s, exploration expenditure dropped drastically and investments in mining developments were also sharply reduced in response to low commodity prices. If this situation were to continue, there would eventually be a shortage of some commodities, which should cause prices to rise, and making exploration and mining of those commodities attractive again. The last few years of the 20th century represented a period of dramatic change for the mining and exploration industry. These changes are still played out, but a new industry structure and way of operating have to be found. Now let us summarize what has been discussed so far. Actually, the mineral exploration, as I discussed, is three-dimensional, that is geological, geochemical and geophysical methods are involved in it. Geological methods include mapping of the structure in which the mineral or the ore is found. This is done with a view to know the geometry of that particular rock body in space, and this will help to estimate what amount of the ore is contained in the rock. The mapping is on the various scales, and it includes very simple process as to asking oneself three questions, that is, where I am, what do I see, and what does it means. Where I am means the location, and what do I see means what I see as the rock, to identify the rock, and what does it means is the geological interpretation. This is the mapping. It can vary from the scale of your and my choice. Next is the geochemical method. Geochemical method is the method which is mostly laboratory based, and in most of the laboratories we find what percentage of the ore is contained in the rock. That means it will help us to decide whether that particular mineral is worth exploring or not. Next is the geophysical methods. Geophysical methods is applicable or is useful where we cannot see the rocks personally. For example, if the rock is in the subsurface, we have to CAT scan that particular surface and find where that particular strata is, or what is the subsurface stratigraphy of surface geology, or behind the underground surface. But this has to be correlated with the geological mapping or the boreholes that are digged in order for the mineral exploration. And in geophysical methods, you employ many of the techniques like resistivity, electrical conductivity, and seismic survey, etc. This is all about the mineral exploration, but the mineral exploration is very important with the increasing population and the mineral need of the society. So I hope you find it useful in your text. Thank you very much.